When encountering a situation where a voltage reading of 680 volts is measured across the fuse or socket ends on the primary side of a 480 volts to 208/120 volts transformer, and this voltage is higher than the supply voltage, several factors need to be considered. Firstly, induction from adjacent live conductors may be the cause. High voltage conductors running parallel to the fuse can induce a voltage across the fuse or socket gap, especially under load. Secondly, capacitance between the primary windings of the transformer can create a voltage potential difference across the fuse terminals. Thirdly, transient voltage surges or power quality issues can temporarily raise the voltage above normal levels. Fourthly, loose connections or open windings in the transformer can cause voltage imbalances and higher voltages at certain points. Fifthly, an electrical resonance can occur in the transformer circuit, amplifying the voltage across the fuse terminals. Finally, ensure that the voltage is measured correctly using a reliable voltmeter to rule out measurement error. When dealing with high voltage situations, safety precautions are paramount. It is crucial not to touch the fuse or socket ends, as the high voltage can be fatal. Always use proper safety gear including rubber gloves, safety glasses, and insulated tools. To energize the circuit by turning off the power supply before working on the fuse or transformer. Maintain a safe distance from exposed conductors or high voltage areas. To troubleshoot the issue, several steps can be taken. Firstly, perform a visual inspection to check for loose connections, damaged insulation, or open windings. Secondly, measure the voltage across the other fuses in the circuit to compare readings. Thirdly, check the circuit diagram and verify that the transformer is connected correctly. Fourthly, if possible, perform a transformer test to diagnose any internal issues. It is also important to understand the possible causes in more detail. Induction can occur when conductors are placed in close proximity to each other. If one conductor carries a change in current, it will generate a magnetic field. This magnetic field can then induce a voltage in the adjacent conductor, even if that conductor is not directly connected to a power source. This effect is more pronounced when the conductors are parallel and in close proximity. In the context of the fuse and transformer, if there are high voltage conductors running parallel to the fuse and its socket, they can induce a voltage across the gap, especially when those conductors are under load, meaning they are carrying a significant amount of current. Capacitance between the primary windings of the transformer is another potential cause. A transformer consists of multiple windings of wire, and these windings are separated by insulation. This configuration creates capacitance between the windings. Capacitance is the ability of a component to store electrical energy in an electric field. In the case of the transformer, the capacitance between the primary windings can create a voltage potential difference across the fuse terminals. This is because the primary windings are connected to the high voltage side of the transformer, and any voltage fluctuations or imbalances can be amplified by the capacitance. Transients or overvoltages can also cause the high voltage reading. Electrical systems are often subject to transient voltage surges, which are short-duration, high-amplitude voltage spikes. These surges can be caused by various factors, such as lightning strikes, switching operations, or the operation of heavy equipment. Power quality issues can also contribute to overvoltages. These issues can include voltage sags, voltage swells, and harmonic distortion. These types of power quality problems can cause the voltage to deviate from its nominal value, leading to higher than expected voltage readings. Loose connections or open windings in the transformer are another potential cause. Loose connections can create a higher resistance point in the circuit, which can cause a voltage drop across the connection. This voltage drop can then lead to a higher voltage reading at other points in the circuit. Open windings can also cause voltage imbalances and higher voltages at certain points in the circuit. This is because an open winding will interrupt the flow of current, which can cause the voltage to redistribute itself in the circuit. Resonance conditions can also amplify the voltage across the fuse terminals. Resonance occurs when the inductive and capacitive reactances in a circuit are equal. At resonance, the impedance of the circuit is at its minimum, which can cause the voltage and current to increase significantly. This effect can be particularly pronounced in transformer circuits, where there is often a significant amount of inductance and capacitance. Finally, it is important to consider the possibility of measurement error. Ensure that the voltage is measured correctly using a reliable voltmeter. Make sure that the voltmeter is properly calibrated and that the probes are making good contact with the fuse terminals. Also, be aware that some voltmeters can be affected by stray electromagnetic fields, which can lead to inaccurate readings. In addition to these possible explanations, it is also important to consider the specific characteristics of the transformer and the circuit in which it is installed. For example, the transformer's turns ratio, impedance, and insulation rating can all affect the voltage readings that are observed. The circuit's grounding configuration, load characteristics, and the presence of any surge protection devices can also play a role. When troubleshooting a high voltage reading across a fuse, it is essential to take a systematic approach. Start by gathering as much information as possible about the situation, including the type of transformer, the circuit configuration, and the history of the problem. Then, use a process of elimination to rule out possible causes. For example, start by checking for loose connections and damaged insulation. If these are not the problem, then move on to testing the transformer and the circuit for voltage imbalances and resonance conditions. Remember that safety should always be the top priority when working with high-voltage electrical equipment. Always wear appropriate personal protective equipment, such as rubber gloves, safety glasses, and insulated tools. De-energize the circuit whenever possible, and never work alone. If you are not comfortable working with high-voltage electrical equipment, then it is best to call a qualified electrician. A qualified electrician will have the training and experience necessary to safely and effectively troubleshoot the problem. They will also have access to specialized tools and equipment that can help them diagnose the issue. When inspecting for loose connections, pay close attention to the terminals where the wires are connected to the fuse holder and the transformer. Loose connections can create a high resistance point, which can cause heat to build up and damage the components. Look for signs of corrosion or oxidation, which can also increase the resistance of the connection. When checking for damaged insulation, look for cracks, tears, or other signs of wear and tear. Damaged insulation can create a path for current to flow to ground, which can be a safety hazard. Use a megameter to test the insulation resistance of the transformer windings. A megameter applies a high voltage to the windings and measures the leakage current. A low insulation resistance reading indicates that the insulation is damaged. When testing the transformer for voltage imbalances, use a voltmeter to measure the voltage on each of the primary and secondary windings. The voltages should be balanced and within the specified tolerance. If the voltages are unbalanced, it could indicate a problem with the transformer windings or the connections. When testing the circuit for resonance conditions, use an oscilloscope to observe the voltage and current waveforms. Resonance can cause the voltage and current to oscillate at a high frequency, which can be seen on the oscilloscope. Use a spectrum analyzer to measure the frequency and amplitude of the oscillations. If resonance is present, it may be necessary to add damping components to the circuit to reduce the oscillations. Damping components are resistors or capacitors that are designed to absorb energy from the circuit. In addition to these troubleshooting steps, it is also important to consider the environment in which the transformer is installed. High humidity, extreme temperatures, and corrosive atmospheres can all contribute to electrical problems. If the transformer is installed in a harsh environment, it may be necessary to take additional precautions to protect it from the elements. For example, the transformer can be enclosed in a weatherproof enclosure, or it can be coated with a protective sealant. Regular maintenance is also essential for preventing electrical problems. Regularly inspect the transformer and the circuit for any signs of damage or wear and tear. Clean the transformer and the circuit to remove any dust, dirt, or debris. Tighten any loose connections and replace any damaged components. By following these troubleshooting steps and taking proper safety precautions, it is possible to safely and effectively resolve high voltage readings across a fuse. Remember, if you are not comfortable working with high voltage electrical equipment, always call a qualified electrician for assistance. They are trained to handle these situations safely and efficiently. Now, considering the 480 volts to 208/120 volts transformer configuration, it's important to verify that the transformer is properly grounded. An improper or missing ground connection can lead to erratic voltage readings and pose a significant safety hazard. Check the grounding conductor size and ensure it meets the requirements of the National Electrical Code, specifically Table 250.122 for equipment grounding conductors. Also, inspect the grounding electrode system to confirm its integrity. The grounding electrode system typically consists of a ground rod, metal underground water pipe, or other approved grounding electrodes. The resistance to ground should be measured to ensure it is within acceptable limits, generally 25 ohms or less, as recommended by the NEC. Furthermore, examine the bonding connections throughout the system. Bonding is the process of connecting all non-current carrying metal parts to create a low impedance path for fault current to flow back to the source. This helps to ensure that overcurrent protective devices, such as fuses and circuit breakers, will operate quickly and clear the fault. Check the bonding jumpers at the transformer, electrical panels, and other equipment to ensure they are properly sized and securely connected. The size of the bonding jumper should also comply with the NEC, specifically Table 250.102 for supply-side bonding jumpers and Table 250.66 for grounding electrode conductors. When investigating transient voltage surges, consider installing surge protection devices, also known as SPD, at the transformer and at downstream electrical panels. SPD are designed to protect electrical equipment from damaging voltage spikes caused by lightning, switching operations, or other transient events. SPD should be properly sized and rated for the voltage and current levels of the electrical system. Selection and installation of SPD should comply with the NEC, specifically Article 280. To further analyze the circuit, use a power quality analyzer to monitor the voltage, current, and frequency over time. A power quality analyzer can capture transient events, voltage sags, voltage swells, and harmonic distortion. This information can help to identify the source of the problem and determine the appropriate solution. When examining the transformer itself, perform a turns ratio test to verify that the transformer's turns ratio is within the specified tolerance. The turns ratio is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. An incorrect turns ratio can indicate a problem with the transformer windings. Also, perform an insulation resistance test on the transformer windings. This test measures the resistance of the insulation between the windings and ground. A low insulation resistance reading indicates that the insulation is damaged. In addition to these tests, consider performing a core loss test. The core loss test measures the power dissipated in the transformer core due to hysteresis and eddy currents. High core losses can indicate a problem with the transformer core. Finally, inspect the transformer cooling system to ensure it is functioning properly. Transformers generate heat during operation, and the cooling system is designed to dissipate this heat. If the cooling system is not functioning properly, the transformer can overheat, which can lead to premature failure. Check the cooling fans, oil levels, and radiators to ensure they are in good condition. It is crucial to consult the transformer manufacturer's specifications and recommendations for testing and maintenance procedures. These specifications will provide valuable information about the transformer's operating characteristics and any specific maintenance requirements. Regularly scheduled maintenance and inspections can help to prevent electrical problems and extend the life of the transformer.